So maybe, what do you think? Should we wait a little bit more for the other students, or should I start? Wait. Thank you. Okay, thank you very much. Hello. Okay, then I think I will start now to not start too late. Anyway, the first part of this class will be again class and a little bit of theory right in the beginning. So it's just to try to understand some concepts more thoroughly. But then I will have more practical parts on overfitting and stochastic gradient descent. So let's start with the theory first, and then we'll have the more useful part when everybody will be there. Okay, so I will share my screen here. Okay. Okay. So yesterday, remember, we spoke about how do we train neural networks, and I mentioned gradient descent as the main algorithm we use. So I explain you a little bit what's behind gradient descent. Remember this curve and the fact that unfortunately in your network the curves are more like this, so it's not easy sometimes to get a global minimum. Okay, I explain you what is a cost function and what do we try to optimize when we train your network. But then I say in the end I said, okay, this is the function we want to optimize when we train neural network, but I didn't say how really we do it. And most importantly, I didn't tell you how do we compute the gradient, because right now I tell you, okay, in gradient descent, you need to update the parameters of the model according to the gradients of this objective function. But right now we don't know how to compute this gradient. So I will speak a little bit about that. Somebody else is coming. And so the first part of today will be about gradient backpropagation. So backpropagation is a key word when you do deep learning, which is why I want to explain a little bit what it means, what is there behind, and also this is key to understand the problems we have seen yesterday when I spoke to you about vanishing gradients. Remember, we did this small experiment on the playground and you redid it on the lab. You take a network with 3 layers and with a sigmoid activation function, and you can see that it does not learn. And when you change sigmoid to ReLU function, it learns. So today we will try to understand why this happens. Okay. So before explaining what is gradient backpropagation, I want to first explain or maybe remind you about the chain rule of differentiation. Okay. So the chain rule of differentiation, because it's key to understand and to be able to compute gradients in a neural network. Okay, let z equal f of y and y equal g of x. Okay, and f and g are differentiable function from R to R. Okay, so we can note that z equals f of g of x. And sometimes we say f with this small dot here, g of x. This means composition of functions. Okay. So if we want to know the derivative of z according to x, in fact, we can have it by deriving the derivative of z according to y multiplied by the derivative of y according to x. Okay. This is the chain rule. Okay, and so in fact, this is this is f prime, the derivative of f evaluated on g of x, and this is g prime of x. Okay, and I don't know in Vietnam how you study this differentiation of function composition. This is more like a uh, Anglo-Saxon notation. In France, at least, we usually state that we usually learn that f or g prime of x equals f prime of g of x multiplied by g prime of x, which is exactly this, right? But we, in France, at least, we learn it this way. I don't know
Yeah,
in
in
Vietnam.
Vietnam we learn that way, but in
Okay.
US we learn the way on the left.
Okay. You know both.
Yeah,
It's useful to know this one because it's easier to relate it to neural networks, as you will see. Okay, so this was just a reminder. Now let us consider a simple neural network. Oh, sorry. Okay, for binary classification. Okay, so in fact, I will copy an image because it will be much nicer. Okay, so you see, you have two inputs. This is my input layer. This is a hidden layer, L1, and my output layer, L2. So I have only two layers, and as you can see, it's a very simple network. I have 4 plus 2, 6 plus 3 parameters, so 9 parameters. Okay, so W11, W12, W21, W22, B1, B2, okay, and then W1, W2, and B3. Okay, and you see here I have written the equation. How do we get y hat out of x1 and x2? Well, we can compute h1 and h2 using these formulas, and then y hat out of z like this. So here is the sigmoid function. Remember, yesterday, one very important thing we've seen is that when you want to do binary classification, you should use a sigmoid function. Okay. Okay. So, in order for the gradient descent to be in order to do gradient descent, we first need to define j of theta. And j of theta is the objective function we want to minimize in order to train our neural network. So, in order to train our neural network to predict our training set, we need to minimize j of theta equals the sum over I of BCE, okay, of yi y at high. So y at high is the network prediction, Okay. BCE, remember, this is binary cross entropy. Remember, yesterday I tell you this is the loss function that we have to use when we want to do binary classification. Then yi here is the label from the training set. And finally, this n here is the number of elements in the training set. Okay, so this is what we want to minimize. And if we manage to minimize that, this means that our prediction yi hat from the network will be very close to the labels in the training set. So our network will explain very well the training set, which is the goal. Okay, great. So we do this minimization. Using gradient descent. Okay. And gradient descent states that we should update iteratively the network parameters Okay, remember the parameters, all of this. So our 9 parameters using this formula. So I noted it theta, remember, theta I should take, I plus 1. I is not the proper true choice because I already used it here, so maybe I would say k plus 1. We'll take theta at iteration k minus alpha d of theta over d of d of j over d of theta evaluated in theta k. Okay, so we need to differentiate this objective function d of j divided by d of theta and evaluate it on theta k in order to be able to update theta k to theta k plus 1. But here, theta is like a set of parameters. In fact, all the theta are there. We have to do this for each individual theta. So we have to do this 9 times, once for W1, one for W2, one for W11, one for W21, etc. So, in other words, we need to compute differential of j over differential of W1 over W2 over B3 over W11, etc., etc. Okay, this is what we need to do. And this is why we will need the chain rule. Okay. How do we do this? We use the chain rule. Okay, let us try. If we want to compute d of j divided by d of omega 1. of W1, sorry. Well, what we can do is we can go back to our equation now and see that J depends on BCE. Okay. So J is basically day of J divided by d day of Y multiplied by day of Y multiplied by d of Z multiplied by d of Z multiplied by divided by d of the balloon one. Okay. You see, I have applied the chain rule. J can be written as a function of Y because it's the BCE applied to Y. Then Y can be written as a function of Z because Y equals sigmoid of Z. And Z is a function of many things, including W1. And in fact, we can compute this. Or we can at least detail what is what. This is basically the derivative of the binary cross entropy. Then this Y divided by dz, if I take here, Y equals sigma of Z. So in fact, maybe to be a little bit more precise, I should write this Y hat here. It will be more comprehensive. Okay, so the Y hat divided by dz is basically the derivative of the sigmoid function. And finally, d of z of over d of w1. This is easy, in fact, because if you differentiate z by w1, in fact, you get h1. So this is the easy part. We can really compute that and say this is h1. Okay, great. So in fact, we can compute exactly the gradient of J with respect to W1. And we can do the same, for example, for B3. So I'll just quickly write it. For B3, we would have d of J divided by d of B3 equals exactly the same beginning. Okay. Multiplied by d of Z. Okay. And in fact, the difference is that here, instead of being h1 because it was derivative of Z with respect to W1, here, with respect to B3, the derivative is 1. But the rest is the same. So in fact, I can do just like this. Okay. So you see, it's not so complicated. Maybe one very small comment is that, remember, here I used the d of Z divided by d of Y, and here I use delta. Why do I use delta here? Is because it's a derivative. It's a partial derivative, not a differentiation, not a derivative over one variable. There are multiple variables, so we use the partial derivative. So this is the easy part. Now let's go for a more complicated part, and let's derive over with respect to W11, for example. I won't do all the derivative. You can relax, but I would just want to do one more. So if I go for 1, and in fact, the beginning is exactly the same. Okay, y hat multiplied by d of y hat divided by z. Then, since I want to go back to W11, I have to partially derivate z, okay, with respect to h1, because h1 depends on W11. So let's go. H1, then H1 partial derivative over Z1, and then partial derivative of Z1 over partial derivative of 1, W11. Okay, so exactly the same idea, but you see, much longer equation. several things I want to say. First, here we still have exactly the same value as before. Then here we have the partial derivative of z with respect to h1. And if we look at what it is, you see that it's exactly w1. So here, maybe I can use the blue. This is w1. Then partial derivative of h1 with respect to z1. What is it? It's exactly the derivative of the activation function that is on this neuron. Right now, I have specified the activation function for the output layer, but not for the hidden layer. Okay, this is because I want to explain you why we had these vanishing gradients yesterday. So I want you to think of what happens if you use this activation function or another activation function. So right now I will just keep f. Okay, f is the activation function of the hidden layer. So let's go. This is basically f prime, the derivative of the activation function of the hidden layer. And finally, d of z1 with respect to w11, let's have a look. z1, w11, it's x1. So the input, which color did I use it? This is x1. Okay, so you see we can compute this this formula because we know all the intermediate steps. And one very important thing to notice is that you see the more you go back in the network, the longer the equation. You can easily imagine that if we had a longer network, a deeper network, okay, with more hidden layers, the partial derivative with respect to the parameters that are very early in the network will have very long equation like this, even longer equation, okay, compared to the one that are near the end of the network. So it doesn't mean that it's more complicated to compute. It just means that the multiplication of these terms is quite longer. And one thing that you can also see is that in order to compute the derivative over the last parameter, we use computation that have been done for the very first parameter. So you see, here the computation is quite small, and the computation for these parameters uses some computations that we have done for this. So in fact, this is why we call backpropagation, because when you compute y hat out of the input x1 and x2, you go in this direction, okay? This is what we call a forward pass. This is the prediction, okay? Forward pass. And then when you want to update the gradients, you go in another direction. This is what we call the backward pass. Sorry. This backward pass means you start from the end, you compute the loss function in the end, and then you backpropagate the gradients. You start by computing this, and for computing this gradients, you use these values. And later, when you want to compute the gradients for these values, which are much more complex, you can reuse what you have computed previously. And if we had more layers and we had even longer equations, we could reuse what we have computed for this for the subsequent layers. You see? So this is why we call that backpropagation. Okay, this is the first remark. Okay, so maybe first remark. We call the training algorithm gradient backpropagation. Because it is more efficient I mean more computationally efficient. To compute the gradients with respect to the parameters of the last layers first, and then the gradients with respect to the first layers last. Okay, this is the first remark. Then a second important remark. The gradient of the parameters in the early layers depends, depends on the derivative of the hidden layers activation function. This is really important. This is exactly what I wrote here. Okay, f prime, the derivative of the activation function, is in this equation. And one even more important thing to know is that if I had more layers, there would be this term several times in the multiplication, because as many hidden layers, if I go back to a previous example, I don't know if I have it here. No, I don't have it here. I'm sorry. If I had several more layers, I would have several more times this product with f prime, the derivative of the activation function of the hidden layers. And why is it important? Okay, remember the sigmoid function. What happens when we use a sigmoid as hidden layer activation function? Well, remember the sigmoid looks like this. Remember, sigmoid is something like this. Okay, this is one. This is sigma x. Now let's have a look at what the derivative of the sigmoid looks. It looks like this. This is sigma prime of x. Okay, maybe you don't really care about that, but in fact you should, because this here is 0.25. In fact, the maximum value of the sigmoid derivative over r equals 0.25. Which is inferior to 1. Okay, Okay, inferior to 1. Why is it important? Because now if you take back this equation and you know that this can only be 0.25 at the most, then you know that this whole product is quite low, in fact, because it's 0.25 multiplied by something. 0.25 at the most, but it can be also very close to 0. And if you remember what I said earlier, in fact, this term can be present several times because you have multiple layers. This means that you will multiply 0 by 0.24, 0.25 multiplied by 0.25 multiplied by 0.25, okay? And if I do this, let me just compute it. I'm not exactly sure how much it does. If I do 0.25 multiplied by 0.25 multiplied by 0.25, this, okay, this is equal to 0.015. Okay, so what this means is if a network has 3 hidden layers with sigmoid activation function, then the gradient is almost 0. Remember, I called the phenomenon that we saw on playground.tensorflow the vanishing gradient. And this is exactly what happens. We say that the gradient is vanishing. Okay. Now, what happens when we use a ReLU function? Okay. Remember the ReLU. What happens with ReLU? Okay. The ReLU function looks like this. And what happens? What does it mean for the derivative? The derivative of ReLU is 0. But here, it's 1. Okay, since this is x, this is 1. And this is very interesting because if the derivative of ReLU is 1, okay, if you have a value, an activation value that is 0, then the gradient is 0. Too bad. But in fact, that's okay because what the network will learn will be to have positive activation function. And when the activation values are positive, then you'll see that the ReLU derivative is 1, meaning this is exactly 1. And since this is exactly 1, then this can be backpropagated. So you remove the vanishing gradient problem. If x is superior to 0, the derivative of ReLU equals 1, which solves the vanishing gradient problem. Okay. If this is very complicated to you, if you think this is complicated, no problem, okay? It's okay if you don't really understand what I just said. What you should really remember now is this is why we should use ReLU activation function on hidden layers. And you can only remember that, and that's all right. I just wanted to explain you a little bit where does this come from, but just remember, if this is complicated, if you think this is complicated, what I just said, just remember that this is the reason why, in fact, it's always a good idea to use ReLU activation function for hidden layers. It doesn't mean that you can't use other activation function, because there are some, and sometimes maybe you can use the sigmoid, but if you want to use the sigmoid function, then it's because you have a very, very, very shallow network. I mean, not deep network. Okay. Okay. I'm done with the very theoretical parts. So do you have question? It's a okay. I understand it can be complicated. This quite a lot of math, but the idea, it's important that you get the idea. In fact, it's important that we get gradients that are not too low. If you don't have any questions, I will go on, and I will speak about more concrete example. I will speak to you about stochastic gradient descent. So I think it's number 4. Stochastic gradient descent and its variance. Okay, so previously here, I explained to you how we compute the gradients. Okay, so now you have all the ingredients. If you had to code it, you could in fact code the optimization of a neural network. But don't worry, because you don't have to code it. Because when you use model.fit in Keras, everything of this is done automatically. You don't have to bother about it. It's just nice that you know a little bit what's inside. Okay, but this is done automatically. So if you do model.fit, the neural network will automatically update the parameters until it works. Okay, this is cool. But in fact, the model.fit does not use gradient descent. It uses a variant of gradient descent called stochastic gradient descent, and I will explain you what is the difference. But even stochastic gradient descent is not necessarily always used. There are some variants. So I will just explain you very quickly what are these variants. Okay. So gradient descent, I'm sorry. Is a useful algorithm. But it has a major drawback in deep learning. We need to compute j of theta, which means the loss on our entire training set. In order to do a single gradient steps. So in fact, this means what? This means that when I want to compute my gradients in order to perform this gradient step, this is what we call a gradient step, I need to compute the derivative of my my objective function j, which is the sum on all the elements in my training set of the prediction of the difference basically between my prediction and my real label. So this means I have to predict with my neural network all the elements in my training set to do only one gradient step. And in gradient descent, you might need thousands of gradient steps in order to converge. The problem is, if you have 100 data in your training set, this is okay. But in deep learning, we may have millions of elements. in the training set. So gradient descent is too costly, too expensive. When I say million of elements, it can even be images, you see. So you will apply your neural network not only to 2 parameters, but to millions of parameters, because an image may have millions of pixels, So the neural network is much more complicated, and predicting one value for one image may be quite a lot, in fact. So of course, this is all optimized on the GPU and stuff, but still, it may be very costly to do only one gradient step when you see the entire data set. So, okay. In practice, we use variants. There are 2 kinds of variants. There is a variant that we call stochastic gradient descent, which updates, which computes, updates compute updates of the gradients, so maybe gradient steps, on a subset of the training set. Okay. And we call the subset a mini batch. Okay. So if we compare stochastic gradient descent versus gradient descents, okay, if the mini batch is of size, let's say m, like this, yeah, m, maybe p will be easier, okay. Then, okay, we call epoch a cycle during which all training examples have been used to update the model. Okay, so in gradient descent, we do one gradient step per epoch, and in stochastic gradient descent, we do n divided by p gradient steps per epoch. So p is the mini batch size, and n is the training set size. Okay, and the only difference if you do this is that, in fact, the gradient step that you do in stochastic gradient descent is not very precise, because you say basically, instead of computing the optimal gradient step, because this is the optimal gradient step, you should use all the elements in your training sets. You take only a few number of elements and you say this is good enough, this is large enough to represent the gradient step for all my data set. So it's an approximation. Okay. When you use stochastic gradient descent, you approximate the real good gradient using only a subset of the training set. Okay. This means that you make imprecise gradient steps, but you make a lot of them. So in the end, what happens is that you compensate basically, and you go much quicker. So let me write that formally. In SGD, gradient steps are approximations of the real gradient steps because they are computed on a subset of the training set. If P is large enough, though, the approximation will be precise enough to maintain convergence. What do I mean by that? If I come back to this, here I said, given a certain theta, I compute the gradient and I go in the opposite direction. Okay, and so when I go in the opposite direction, I get closer to my optimal solution, and then I go back again. But what happens when you do stochastic gradient descent is that this gradient that you compute is actually false. You compute maybe this. This is not the right gradient, and it's not the right gradient because you are not computing it on J, but on something that is different of J because it depends on only a subset of the whole training set. But you see, even if it's imprecise, it's in the same direction, okay? So if I go in the opposite direction, I still end up around here. So even if it's imprecise, it is precise enough so that I can converge, I can go towards my solution. But suppose now that my gradient is like this, then if I follow the opposite direction, I go there and I diverge. I do not converge towards the solution. This is what I mean. But usually, if you take a batch size that is large enough, you can converge towards the solution. Okay, so this is what I mean by this sentence. Okay. Okay. Great. Now I would like to speak a little bit about momentum. So, in order to improve SGD efficiency, one can use momentum. Okay. This helps converging or maintaining convergence when the gradients are particularly imprecise. Okay, so suppose you go from here. Okay, this is your theta 0. And this is your optimal theta. Theta star. Okay, optimal. Gradient descent would do this. 1 step, 2 steps, and 3rd step. Okay, this is gradient descent steps, which are optimal. And now, if you go with stochastic gradient steps, you will have something like this. These are stochastic gradient steps. They are unprecise, but they still help you converging. Okay. When you use momentum, what you do is that you will take into account the previous gradient. Okay. So this iteration, you go there. And the next iteration, you should go there. But if you take into account the fact that at the previous iteration, you went there, then you will correct this and you will do something like this. Okay? Because it's this direction, but corrected with this gradient. And then for the next one, which should go there, if you take into account the fact that last time you went there, then you will do there. Okay? So what happens is that with momentum, so in the beginning you do this, okay, so this is SGD with momentum. Okay, so momentum is a technique that uses the previously computed gradients to correct the update. Okay, how do we do this? Instead of doing theta I plus 1 takes theta I minus alpha like this, do something like V I plus 1 like this takes Vi minus 1, Vi, okay, minus alpha, okay, and then theta I plus 1 takes theta I plus Vi plus 1. So V here stands for velocity. It's kind of the inertia of the momentum. And the mu here, parameter, it's called the momentum parameter. And when people use momentum, usually they set this parameter to 0.9. This is a good value. It has to be between 0 and 1. When it's close to 0, this means that we don't use the previous gradient. And when it's close to 1, it means that we use a lot the previous gradient. So 0.9 is kind of a standard value for momentum. Okay. And then final things I want to mention is adaptive learning rate. Okay. Okay. So the idea of this is, instead of having a constant learning rate, we can change the value, its value, over time to be more efficient. Okay. So let me illustrate this. Suppose you have this, or no. Suppose you have this. Okay. If you have a constant learning rate, initially you will do large steps like this. Okay. And as you will continue, you will do smaller and smaller steps. Why? Because here you see that the gradient is slowly going towards 0. And so, in fact, the steps are getting smaller and smaller. So this is without adaptive learning rate. Now, if you want to use adaptive learning rate, here is what we can do. In the beginning, the learning rate is large, and this is good. So here in the beginning, large learning rate. I mean, normal learning rate, sorry. But here, as you go down, the normal behavior for the gradient step is that you do smaller and smaller gradients. But when you reach this part, you see that it's almost flat, and so you will not evolve anymore. You will not go towards the minimum if the minimum is somewhere here. Okay, suppose you have this here. You want to go there, but here you get stuck because this is too small, and you won't do large gradient steps. So what you can do, if you want to continue evolving correctly, here you can increase learning rate. To compensate the small gradients. Okay, this is with adaptive learning rate. So using adaptive learning rate will typically do two things for you. It will help you converge faster towards a good solution because you won't get stuck in this, what we call in this plateau, basically. And also, when you reach a good solution, when you are getting closer to the solution, adaptive learning rate will also become smaller so that you can get a more precise value for the solution. So adaptive learning rates are usually a good idea. Okay. And there are several optimizers that have automatic adaptive learning rate. One of the most famous is Adam. Okay. Adam is one of the most used optimizers which adapt automatically the learning rate. Okay. So why do I tell you this? Because you'll see in the lab, if you remember correctly, I use the SGD optimizers, which is the standard thing to do using SGD. But if you want to be more efficient and you want to more quickly get a good solution, it's a good idea to use Adam. Okay, so there are many others. I won't comment them all because it's not. I mean, so interesting to explain very in detail why some are better than the others. But usually, when you want to prototype, it's always a good idea to use Adam. And later, when you want to really get the best performance, then in fact, people tend to use SGD to get the best performance. But it takes longer and longer runs to get good performance with SGD, whereas with Adam, you can go quickly towards a good solution. So it's good to prototype. So Adam is a good choice in general. This is what you should remember. Okay. I'm done with optimizers. And now I would like to speak to you about overfitting and underfitting. This is probably this is okay, 5. This is the final part of this class. It will take me maybe 45 minutes. I have a small request, if that's okay. Can we take a 5 minutes break right now, please? Because I need to go buy a sandwich. I have nothing to eat.
Okay.
If that's all right, I come back in 5 minutes. Okay.
Okay.
Thank you very much. Sorry. Okay, I'm back. I'm back. Sorry. Thank you for waiting. Okay. So in order to explain to you a little bit what is underfitting and overfitting, I will have to do first a few definitions. Okay. And then it will become, I hope, more concrete. And I hope we will have time this week in the labs to really make you understand what are these overfitting and how you solve it. Okay. So now we have seen how to train a neural network using SGD. And we have formalized the problem of training a neural network by the minimization of a function j of theta that we defined previously. Okay. Another name for j of theta is empirical risk. Okay. Empirical means based on experience. Okay. This is the idea. Why can we call j of theta empirical risk? Is because, in fact, the j of theta is computed on a training set. A training set is something that we gathered. It's experience basically for our task. It's experience that we have on our task. Okay. So based on experience, on available data. Training set. So empirical risk meaning it's the risk that we make using our current neural network. It's the risk that we take to make mistakes on our training set. This is empirical risk. This is just a reformulation, a renaming, okay, of what we have called earlier objective function or mean average of cost function over all the training set examples. Okay. But in fact, even if that's something we want to optimize, we do not care. It's important to understand that about empirical risk. What do I mean by that? What we really want to optimize, okay, is not the function or the neural network evaluated on the training set, but the neural network evaluated on the whole set, which is a known of possible data and labels. Remember, I told you earlier that our neural network is a predictor. okay, that allows you to associate data from a space that is X to labels that from a space, okay, this is our neural network. But in fact, the empirical risk allows you to say that you are doing a good job on the training set. Okay, so your neural network is able to associate any X with any Y, but you just know that it works well on the subset that is called the training set of X and Y. You see what I mean? So it's not because your neural network is good at that he will also be good at the rest. What's the performance there? We don't know. Okay. So how can we formalize this? We call expected prediction error EPE. So EPE. The cost function evaluated on the whole unknown set of possible couples of data and labels. So if formally, if X is the space of data, Y is the space of labels, and D equals xi, yi belonging to x cross y at the power of n. Okay. The training set. Then the empirical risk is equal to the sum of I equals 1 to n, okay, of the cost of yi y hat I, okay, and the expected prediction error equals the sum over x and y of the cost. So it's exactly the same formula, except that this should be computed on a much larger number of data. And in fact, we do not have the data because we don't have all the possible pairs of data and labels annotated. We have only a very small set that is called the training set. Okay, so we cannot compute this. This is very important to understand. We cannot compute it, but this is what we really want to optimize. ER is interesting. It gives you a hint as to whether your neural network is good or not. But what you really want to know is your neural network good at this EPE? Okay. One thing that is interesting is a low EPE implies a low empirical risk. Okay. Low expected prediction error means a low empirical risk. But does a low empirical risk necessarily implies a low EPE? No. Okay. So the whole process of machine learning, because this is not specific to deep learning, it's specific to machine learning in general. Okay. The whole process of machine learning is actually flawed because we want to minimize something we don't know, and for that we minimize something, the empirical risk, that does not guarantee that in fact you minimize the expected prediction error. Okay, so this is a very a big problem, in fact, when you do machine learning. Okay, so more definitions. A high empirical risk is called underfitting. So underfitting means that you did not manage to properly learn our training set. Okay. And underfitting also means we have a high EPE, okay, which is not desirable. So what I mean is we want to avoid underfitting. But conversely, okay, sometimes we may have a low EPE, a low empirical risk. Okay, so low empirical risk means a good performance on the training set. Okay, but a high EPE is a bad generalization. This is called overfitting. And it means that our model is so good at predicting the training set that it is over specialized for this data. Okay, let's take an example because this might be a little abstract. Look at this figure. This is a very classic figure. So the blue points that you see here, those are the training set. Okay. Okay. And the curve here, basically those are three different models that we train on the training set. Okay. The first model is a line. It's only a line. And as you can see, the first model does not really explain well the points. It does not really relate X to Y very good. So this is bad, actually. This is a bad model. And remember, I say basically the empirical risk, so the objective function, the fact that our model explains well our data, okay, the objective function is very bad, and so we have a high empirical risk. Okay, so this means that we are underfitting, considering what I just said. Now here, the exact opposite. We have a very good model for ER. So a low ER. Okay. Why? Because you see that all the points are extremely well explained by the model. The model really fits the data perfectly. Okay. But now suppose I'm adding a new data, a data for which we have not trained the model. So suppose I add the data here. Okay. You see the data here. It seems reasonable because we can see that it's pretty much aligned with the other data. So here you see that the EPE, the expected prediction error of our model on this new data, is quite bad. Okay, we will do a big error on this new data. So we have also a high EPE. And here we have a very high EPE. You can see that here on this point, the error of the model will be very big. And this is called overfitting. Okay. Now, here, the model that we have here looks correct. It explains the points quite well, but it also very good on a new point. Okay. So we are neither underfitting, neither overfitting. We do just have a very good model. Low empirical risk and the low expected prediction error. Okay. So here, in this example, you can see something very important. You can see that the capacity of the model has a huge impact on underfitting and overfitting. What is the capacity of the model? The capacity of a model okay, designates its ability to model complex problems. Here we have a model with a low capacity because it's only a linear model. It's very simple. Here you see that we have a model with a large capacity. It's a polynomial with a high degree model. And here we have a model of average capacity. So it's actually well adapted to the problem. Okay. So here we have a small capacity. And here we have a large capacity. Okay. So finding the right capacity has a direct impact on EPE. Okay, and so on underfitting and overfitting. In deep learning, the capacity of a model depends on its depth and number of neurons. Which means its number of parameters. Okay, just another quick figure. And then I will try to illustrate the problem of overfitting on a real example. Just another way to show this, what I just wrote, is to see this. Okay. This is basically empirical risk, and this is basically expected prediction error. Okay. As you can see, here you can see the model capacity, and here you can get the error of the model. So you see here we have models with a low capacity, and here we have a model with a high capacity. So there is a zone here that we call underfitting zone, for which the empirical risk is still very high for the model. So we have a model with low capacity. We are exactly in this case. Okay, the model is too simple, and so we cannot really optimize our model on the training set. And so, of course, the expected prediction error is also very high. So this is the underfitting zone. Now, if you increase a lot the capacity of the model, then you can decrease a lot the empirical risk. This is this case. You can have a perfect fitting of your training data. But the problem is, if you do this, you'll get a high EPE. And this is what happens here. You have a very low empirical risk, but a high EPE. So the right capacity is somewhere here. Okay, you have low empirical risk, quite low EPE, and this is what you really want to find. Okay, so finding the right capacity for your neural network is actually very difficult. Okay, let me do a small pause, a small break. I want to show you again the playground.tensorflow.org. Okay. Okay. I will change my window. Okay, I will now present this. Okay, remember we saw this yesterday. So what I want to show you is what does overfitting means. And to show overfitting, let me show you first this. Here you see that I am creating a lot of noise in the data. And since I have noise in the data, the good answer is still something. I will put a value and I will remove this. Okay, and I will put more neurons. So if we train with a model that has quite a small capacity, you see that it's not the regular shape that we had yesterday when there is no noise. If I remove the noise, you see that the model has a nice shape. Okay. Now, if I put a lot of noise, you see that I don't have a very regular shape, but it's still okay. But now what happens if I give a very high capacity to my network? How do I do this? I can add layers. and I can add neurons. You see here, I'm going to the maximum. So here the maximum is 6 layers, I think. Yes. What happens? Let's have a look. Okay, network is learning. For now, it's okay. But let's wait for a little bit more longer. Here, the model is still trying to optimize the empirical risk. So it's trying to fit the data. But the model is very complex. It has a high capacity. So it is able to actually fit the data more than what it's doing right now. And you will see that the region here, the prediction region, it will be distorting a lot. I am waiting for more time because it takes time. But you will see this. And in the meantime, I want just to say that this is what you will have to show in the lab works for question 3 and 4. This is what I mean when I say you need to show the overfitting. Okay. So let's wait for a little bit more. But what you can see here is that the shape of the region is not regular anymore. You have the region that is trying to go there and there as well. And it should try to go there and there as well. So you see, it's very, very ugly. And if I wait a little bit more, it will become even more ugly. Okay. So what I'll do is that I will do a screenshot. Okay. And while it is learning, I will get the screenshot and put it in the document, just for you to remember. Okay. Okay, as you can see now, it's very, very, very distorted. Okay, I will stop there, but you see the end. I hope you get my point. Okay, so I'm going back to the example. To my document. You see that I have copied this, so that to show you that this is an example. Okay. So now I want to tell you a little bit of how can you detect overfitting. Okay. So there is a good practice when you want to detect overfitting. It is to use several different training sets. I mean, several different label sets. Okay. When you have training sets, usually, okay, so I will change my. Okay. How can we detect overfitting? Okay. So what we'll do is that in practice, we split our labeled data into 3 sets. Remember, earlier I said this is our training set. We have a small fraction of labeled data from the whole space. Okay. Well, this small fraction of labeled data, we will even split it more into 3 different sets. So this is our labeled data. And what we'll do is that first we will use a training set. On the training set, is used to optimize the parameters of our model. What are the parameters of the model? It's the weight and biases of the neural network. Okay, this you know already. Now, why do we need two more sets? It's a little bit technical. So before I explain what is a validation set, I will explain what is a test set. Okay. The test set introduces new examples, labeled examples, to evaluate how the network generalizes. Okay. So it is approximating EPE. Okay. Approximating EPE. So if I go back to my curve here, remember I said, okay, we have a high empirical risk, a high EPE, but sometimes we have a low empirical risk, and sometimes we have a high EPE, sometimes we have a low EPE. So we need a way to know when we are here and when we are here. And a way is to basically show this curve, show the difference between empirical risk and EPE. But as I said earlier, we cannot compute EPE. We cannot compute the expected prediction error, meaning what will be the error on the new data. We cannot compute it, but we can try to estimate it. How? We can have a set of data for which the model has not trained on. It's exactly my green data here. The model has been trained on the blue data. Okay. And on this blue data, the model obtains a performance. This is the empirical risk. And now if we show new data, this green data here, the test set, then we can see, okay, how does the model perform on new data? And this is a way to try to understand what can be the EPE on this new data. So the test set is useful for that. Okay. So you could say, okay, we have our training set, we have a test set, then we're done. But then in fact, we need a third set. And this is a little bit technical. We call this a validation set. The validation set is used to optimize the hyperparameters of the model. What are the hyperparameters? Well, when I say we have weights and biases, this is parameters of the neural network. But in fact, it's not enough to say that we have such weights and such biases to formally define the neural network. To define the neural network, we have to say that, for example, if I go back to one of my neural network here, we have to say that we have a neural network with a certain number of layers. The depth of the neural network is a hyperparameter. We have to say that for this layer, we want, for example, 5 neurons. This is a hyperparameter as well. The parameters are the values of these weights and biases, but the hyperparameters globally define the type of model we are using, or also it defines maybe the learning rate. learning rate is a hyperparameter. Remember the learning rate, my alpha in my gradient descent, this is a hyperparameter. The momentum is a hyperparameter, okay? So these are all choices that we need to make in order to train and to create our neural network. But these choices, they are not really learned on a training set. What is learned on a training set is the weights and biases. So we need another set in order to say those choices that we made for depth, for depth, okay, depth, number of neurons per layer, or for learning rate, or for momentum, or in fact there are more. We will see some other in a few seconds. Well, those choices are good or not. We have to be able to say that. And how do we say that? Well, typically what you do is you choose a set of hyperparameters. Okay, you say, okay, I will use depth equal 5 with 5 neurons per layer. My learning rate will be 0.01 and my momentum will be 0.9. And then this helps you creating a model that you will train on the training set. And this will give you some performance, and you can evaluate the performance on the validation set. And then you can change the hyperparameters and evaluate the new hyperparameters on the validation set. And so across all the type of hyperparameters you can choose, you can say, okay, on my validation set, my best set of hyperparameters is depth equal 5, number of neurons is 6, learning rate is 0.005, etc., etc. You get the best values. And once you have that, you can finally evaluate your overfitting based on the test set. So training set, optimize parameters. Validation set, optimize hyperparameters. And test set optimize gives you basically a sense of how well you generalize. Okay. So now we know how to train a neural network and how to evaluate if it is overfitting, underfitting, or not. But how do we correct overfitting? In fact, we use something that we call regularization. Okay. So that is the last part of today's class. It's 1:30. It's 7:30 for you guys in Vietnam. What do you want to do? Do you want to have a small break, or do you want to keep going with the class?
I think we can have a small break so that people can return home from the office.
Okay. Okay. So let's have a break until 8. Is that okay?
Yes.
Okay. So we have the break. Then we can speak about regularization strategies. Okay. And then we can go to the lab. Okay. See you later.
See you.
Drive safe. Okay, I'm back. I hope everybody arrived safely home. So, if that's all right with you, I'll start back with the regularization. I think it's 20 to 30 minutes, and then we can go on with the lab. Okay. Okay. So, regularization is a sorry. Regularization, not easy to say, is a set of techniques that help reducing overfitting. And before I speak to you about some of this technique, I won't say everything, but some of it. I just want to tell you that the number one technique, the number one thing you should do when you have overfitting, in fact, the first thing to do and most efficient thing to do to prevent overfitting is to increase the size of the training set. This means add more data. Okay, so I mention it because it's very important, but it's obviously not a technique. But in fact, when you have overfitting, it helps a lot if you get a little bit more data. Okay, because for example, if I take the overfitting that is described here, you see here we have overfitting, but what you can see is on this part of the space, the prediction is not perfect, but it's not bad. Okay, if I compare to this, the overfitting is not a big problem on this part of the region. Where it's a real big problem is on this part of the region. Okay, and here, suppose you have added this data to your training set, most likely the function will not learn something like this, but it will learn to be much more better in this region. So in fact, you will reduce overfitting a lot if you had added this data or a little bit more data. Okay, and it's true in general. Like overfitting is usually due to the fact that you have not enough data to learn a lot of parameters. Okay, in a deep learning network, usually you have maybe thousands, sometimes millions of parameters. And if you have only a few data, a small data set like 1,000 of data points, it's too little to learn that many parameters value. So the first thing you should do if you have overfitting is probably to increase your data set. Increase your data set is not easy because it means that you need to annotate data, and so it costs money. Okay, so sometimes it's just not possible to add more data, but if it's possible, that's definitely the first thing you should do because this is what will help you the most. Okay, now the thing is, usually it's not possible to do that, so we have to find other ways, and other ways is regularization. Okay. The first regularization technique I want to tell you about is weight decay. Here are the most common regularization strategies. Weight decay. Okay. In weight decay, we change the objective function in the following way. So remember, the objective function is j of theta equals the sum of I equals 1 to n of the cost of yi y at I. Okay, this is the usual j of theta, and in fact this is, remember, empirical risk. Well, what you can do is add a certain term that you will typically write like this: lambda norm of w, or maybe I can just put theta. Okay, so this is y decay. So why is it called weight decay? First, let's analyze a little bit this. So you know that j of theta is the function that we will minimize during training. Okay. So during training, we will try to make this as small as possible. Before, we only try to make this as small as possible. And so what happens is, if this is becoming too small, this is the curve here. If the empirical risk is becoming too small, then it means that we are starting to overfit. And so EPE must be large. Okay. And so we are not happy with that. So what happens is that since we are trying to minimize two things, and those two things are completely antagonist, I mean adversarial, okay? When this diminishes, this increases. And when this diminishes, this increases, okay? You cannot have both value towards zero, it's not possible, okay? So since we are trying to minimize this and this means that we cannot put that too small. And since we cannot put that too small, we cannot really overfit. That's the idea behind this. And I was saying, okay, these two are adversarial. Why? Because this theta here, remember, it's weights and biases of the network. Okay. So suppose you manage to minimize completely this, meaning all your weights and all the biases of your network are zero. What happens? Let's go back to our neural network here, for example. So you see, this is a neural network. These are weights. These are biases. And suppose that all of these are zero. What happens, basically, whatever the input that you will make, you will always predict zero here. Okay, so your neural network will become only a model that can predict only zeros. And this is bad. Of course, this is really, really bad. Okay, if you want to be able to predict complicated behavior for your data, you need those weights and those biases to be able to evolve a lot. Okay, and so, sorry, and so if this is zero, okay, if lambda okay, tends to 0, then in fact the empirical risk tends towards infinity. Okay. Whereas if the empirical risk tends to 0, then this increases, or maybe not completely goes towards infinity, but it's just to show you this. Okay, I hope you understand the point. So this means that basically minimizing the sum of it will find some kind of balance between minimizing the empirical risk and minimizing the weights of the network. Okay. So a word about the lambda. Lambda, oh, sorry. So lambda is basically a regularization. I don't remember how they call it here. Rate, okay. So if lambda equals 0, then there is no regularization. And as lambda increases, it forces the model to get more complex, less complex, sorry. And so the empirical risk to be degraded. Okay. So maybe this is a little abstract to you. So what I want to do is show you a little bit what it does. I'm going back to the playground TensorFlow here. So remember earlier, I created data with a lot of noise. I created a large neural network, and while training it, you see that there is a huge overfitting. By the way, this shows you the overfitting because you have the training loss and the test loss. And the test loss is the black one, and the training loss is the gray one. So you can see that the test loss is getting bigger and bigger, while the model is getting better and better on the training set. So in fact, the model gets worse and worse at generalizing. So the EPE is worse and worse. Okay. This is the kind of curve that we look at in order to detect overfitting. Overfitting is basically the fact that you have a huge difference here between those two curves. Now, if I want to avoid overfitting, I can add some regularization. So let me try to add very small regularization. Okay. Here is what happens. Okay. So in the beginning, we get a nice region, and we have to wait a little bit. One thing we can see when we look at the curve here is that the curves are a little bit distant. So you see that there is a slight overfitting. And when you look at the region, I don't know if you see it well on the video, but the region is trying to distort a little bit, but it's limited. Okay, it's still distorting, but for a reason, the regularization rate that I used is too low. Okay, and so here it does not prevent overfitting. You see here we can really see that the overfitting has started. So let's stop and let's try to put a higher regularization rate. For example, this. Okay, so you see the region is still regular. And now let's wait a little bit to see if we manage to overfit or not. it seems to be stable, right? From what we see on this curve, the test loss does not get far from the training loss. So this is an exact case for which regularization helped. You see that the region is still quite regular, okay? And very interesting, look at the weights in the network. You see, most of the weights, they are almost transparent. They are very small, towards 0, 0.016, 0.018. And this is exactly the effect of the regularization. Remember, it puts all the weights, it tends to put the weights towards 0. Okay. Now, let's use a larger regularization, just to see what happens. So, you see, not so good. What happens is all the weights are 0. Okay, you can see almost 0. And if all the weights are almost 0, our network can only predict 0. And so you see, the loss is really bad. Okay, so it's very interesting to see this because you see all the possible things that can happen with the regularization. Either it does not work at all, and it prevents the network from learning. Okay, or it can work, and it prevents the network from overfitting, but the network can still learn, which is exactly what we want to do. Okay. And last, and worse, it doesn't do anything. So you don't regularize enough, and so you overfit, and so you didn't manage to solve the problem. So this is exactly what I want you to do in the lab. For the last part of the lab, I want you to try to show me that regularization works in Keras. So in Keras, the regularization is called kernel regularizer. Maybe I can come back to my no, sorry. So in Keras, we can use kernel regularizer to do regularization by weight decay. Okay, great. Now I briefly mention 2 to 3 other types of regularization, and then I leave you with the class because it's a lot already. Let's speak about data augmentation. Okay. When it is not possible to add data in our training set, we can artificially create new data by applying transformation to our learning set. Okay, let me try to illustrate this with a figure because it will be much clearer than anything I can say. Here. Oh. Oh, sorry. Okay. Sorry. Sorry, I have a problem. I have a bug. Okay, let's try one more time. Okay. So you see here is an example. You have one image that shows this little animal. I don't exactly know the term in English. And you have a lot of transformation that have been applied to this image. Okay. And the good thing of that with that is that even if those transformations change the image a lot, the object that you can see on the image is still the same. It's still the same animal. And so the network should still predict that this is the same animal over all these images. So even if for us it seems to be always the same example, for the network it makes enough difference to learn better and to think that this is some kind of different images. Okay, and this is the whole point of data augmentation. Okay, so in practice, data augmentation is used a lot in image processing. But cannot always be used elsewhere. Suppose you are doing text processing. What kind of transformation can you apply to a text that will keep the meaning? It's difficult because, for example, in French, if you say two words, one before the others, it might be a different sense than if you switch the order of the words. So you can't really apply transformation that you are certain will not modify the meaning of the sentence. Okay, so in text processing, for example, data augmentation is not really used. And in fact, it's in image and audio processing that data augmentation is the most used. But still, it's a huge regularization strategy, very important in image. So this is why I wanted to tell you about. Okay, then we have dropout. So in dropout, we randomly turn off some units while forwarding step, while predicting data labels. This prevents the output to depend too much of one particular path in the network. So let me be clearer. I have also an image. Suppose this is your network, okay? Okay. This is your network. Instead of using this network to predict the output out of the input, you will use one of the sub-networks. So for example, this one, you will use only this, okay? And you will train using only this. And what happens is in that case, you will force the network to learn a little bit how to predict y with only x2 and h2. Okay, so only use subnetworks for prediction and training. So you will force the network to understand that sometimes with only x2 you can already make some prediction. Okay, sometimes you will only use h1, x1, x2, h1, and y. You see, so this will help you learn more redundantly, and so prevent overfitting some parts of the data. Okay, and I have a final strategy that is called bagging. Okay, and the idea here is to train several different models at the same time. Okay, and make them vote for the prediction. Okay, the idea is that different models might make different errors. So suppose you have like 3 models. Okay, model 1, model 2, and model 3. And you have the same output, x. Okay, and you will have y hat 1, y hat 2, and y hat 3. Well, you do some kind of combination of y hat 2, and y hat 3 to get the prediction. For example, if this says class 0, this says class 1, and this says class 1, then the bag of model predicts class 1. Okay. Okay. This is a long class. I'm sorry. And also, I'm sorry to write that much. Tomorrow and the day after for the class, I will have slides. I have worked on translating some slides so that it's easier for you to follow than only bad written text. Okay. So tomorrow you will have slides. It will be better, I think. So right now we are done. What I want you to do now, maybe I can go back to the lab work because I want to show you a little bit what you need to do. Yesterday, I know that some of you have already started to finish to do what is necessary to do right now. So I want also to give you a little bit more work so that you are not bored. Okay. Okay. You are not seeing my collab, right? I will share it with you. Okay. So you can see my Google Colab. Hello? Can you hear me?
Yes.
Thank you. Thank you, Doug. So if you see my Google Colab, remember yesterday you have tried changing this in order, for example, to show the vanishing gradient. So as I explained earlier, if you have a neural network with a large depth and sigmoid activation function on the hidden layers, you will observe that the network is not learning. and you can solve the vanishing gradient problem by using ReLU activation. Okay, so just one thing, because some of you didn't do it, I want you, when you answer the assignment, I want you to do it after this. I don't want you to modify before, because I cannot see the evolution of all the questions. So I would like you to do something like this. You can say, for example, exercise 1, okay, and then you put some code here like this, and you can recopy the model here, and you change it according to what you have to do, and then please also add the code for training, so that I can see that during the training it works like it is expected. You can even also add a little text to explain what is happening. Okay, so please just do that to make for me easier correction, so that I can have enough, all the thing is contained into the same notebook. Okay, so I have already said it to some of you by email when you sent it yesterday to me, but I say it again. Please make everything available in the same page. So today, mostly you will have to do this. So exactly what we said about regularization. You can create a large neural network, okay, with 8 layers of 10 neurons, and try to overfit the training set. So to see the overfitting, you need to print this curve. You remember this curve here? You have validation error and training error. I'm sorry, it's in French, but you can change it here. It's validation error and training error. Okay, and so I want to see, you remember the curve that shows that we have a validation error that is too big compared to training error. This is what I want to see that you manage to overfit. And then once you manage to overfit the training set, I want you to add weight decay. So like with the kernel regularizer parameter, you have example given in the link here, to limit the overfitting. This is the assignment I want you to have done at the end of the class. Now, if you finish very quickly, which is possible because this is not so complicated, there are a few more things that I want you to do. Okay, so that you have enough work to to get busy. Okay, so I will write it in the chat of the meeting. The 5th assignment, it's optional only if you have finished the 4th one before the end of the day. If you have not finished today, then you don't have to do the 5th, but please do it right now if you have time, because it's I think it's interesting. I want you to try different learning rate. So please train a simple neural network, meaning 2 hidden layers of 4 neurons each, with 4 different learning rates. Okay, I want learning rate equals 1, learning rate equals 0.01, learning rate equals 0. Maybe like this, 0.001, and learning rate equals 0.00001. Okay, and please plot the training loss evolution of the 4 learning rate on the same curve. So what do I mean by that? I'm sorry, I will still change. No, I can change this. I mean that I want basically a curve like this, okay, where you will have, for example, here the training loss evolution with a certain learning rate, like okay, sorry, it will be easier like this. I'm doing it with the mouse. Let's do it like this. We equals 0.01, and maybe you can have this with LR equals 0.1, etc., etc. Maybe you will have this, or maybe you will have this. Okay, something like this. So this is the kind of curve I would like to do. I would like you to do in this not mandatory in this not mandatory assignment. Okay, is that clear?
Yes.
Okay. Okay. Then you can start the lab again. Please correct the labs that you have done yesterday if it does not fit what I just said, and then you can continue and please ask me questions on the chat or verbally if hello.
Hello.
It's better.
Because what was going on? You were speaking, right?
I don't know what happened.
Yeah, this
Okay.
kind of
Okay, great. Okay, so it's clear for everyone what you have to do. How are you doing? Do you have any question? Please do not hesitate to ask me. I'm here for you.
We are working together.
Okay. Yeah, I have received. I just replied. Did you receive my reply? Because you have a small bug for the end. This is why you have the problem. You're welcome. Okay, everybody. I have another class now. I'm sorry, I have to switch class.
Yeah, teacher, I have a question.
So just to tell you, tomorrow we will start convolutional neural network. So on image processing, which means I will also give you a second assignment more on images. Okay, so for this one, I hope you all finish the part on regularization. If you haven't done the 5th assignment, it's okay. So I give you until the end of the week to finish this assignment, and tomorrow we will start the project. Okay.
Yes.
Okay. So tomorrow let's meet at 5:30 if that's all right with you, and see you tomorrow.
Yes. See you.
Yeah, thank you.
Thank you. Bye bye.
Bye bye.